I'm sorry?
Is this our router here?
Yeah, yeah. So if the other router doesn't work, try this one. I have no idea. Also, for some reason, they did something with the certificate that it supposedly works with Chrome but not with Firefox, and that's been my experience too. So, okay. Any questions? Yeah.
Last question in Control C3.
Uh-huh.
Did you say anything about the finish the lab?
Um,
Or have you really decide whether you finish it?
Okay. Well, I guess not having decided anything, you don't have to finish it. Yeah, it's okay. You don't have to finish it. Yeah, if you want to, but you don't have to. I'll give a homework with actors, and that'll give you. No, I'll post it tonight. That'll give you enough to do with actors.
So when you say skip it for the exam as well?
No. I mean, the final will have some question on actors on it for sure.
So what?
But I'm saying you don't have to like take off your precious time and finish the lab. There were some lab questions that we didn't get to, like no one got to them, that had to do with React, and so I'm not so interested in React that. No, it's a fair statement. React is kind of an implementation detail in Scala that I mean I don't think it's necessary for understanding the basics. Other questions? You had a question.
Oh, no, I was going to ask about the slides. If how many for the lab? How many is the number? Like 3 or 4 steps?
Yeah, I mean, you whatever you think you kind of need. What was your topic?
The C#, the generic types.
Oh, I see. So what do you want to show? And you want to show something with variants, I suppose, and there's some stuff that doesn't compile and fix it. Yeah, I mean,
yeah,
a few steps that
we create 3 slides already, so we have steps that relate on different topics and stuff. So,
I mean, I've got to leave it to your judgment. You know how long the labs are when I do them, and so that's an upper bound.
Right.
So how many do you so in the presentation we are supposed to cover the topic and then go over the labs as well?
That's right. You're just going to give a brief presentation and say this is what the lab is about.
And not demo.
It's up to you how you want to most effectively present. Yeah.
How long are the presentations? Just to get like a time.
Like 15-20 minutes, I would think.
Including the lab.
Yeah. No. We have what? We have 7 teams.
So you're doing it in 2 days, right?
And we have it in 2 days. And so what's 75 divided by 4 is not quite 20, right? And so I guess each of you could have 22 minutes if we can get the middle team to break it up into 2 days, which seems awkward. So realistically, each of you is going to have more like 17 minutes, right?
Like 15 minutes.
Yeah.
15 minutes, 4 minutes per slide, 27.
And so if you feel that there's more, I mean, it's unlikely that you're going to have more slides than that. If you feel that it needs more technical stuff, then you can just say this is the technical, this is the syntax that one would need to know, and I've prepared these 2 slides with that syntax. You don't have to laboriously go through every little parenthesis. If you find that you're short of time. I mean, what I'm interested in is, can you tell me the essence of what's going on? And I can always review your slides and your labs at my leisure. But I'd rather have you focus on what that one interesting point is, and just don't spend a long time on what's peripheral to that.
If we have these in our individual repos
Yeah,
and our project.
yeah, exactly. So I would download. When am I supposed to look at them? Okay. So I will download them tomorrow
Okay.
and review them. And I know I owe you homework too. Okay, other questions? Yeah.
So when you said we have to have it in our report,
Yeah.
so the person who is doing lab has to have the lab report.
Yeah, that was kind of the idea. Yeah.
So we are kind of facing problem with the IDE, so we haven't got with the lab yet, and we're supposed to meet with
Well, then you just have to put in a note and say the lab isn't ready yet. What can you do?
um,
Which IDE?
Newspeak.
Oh, I see.
So the IDE, we'll just
Oh.
because
Okay. I can send you an email of a guy who's a student here who's working with Dr. Pierce on his master's project with Newspeak. He might be able to help you get that. Other questions? Okay, let's get on to it. So we're going to be talking about the fork join framework today. So it's a Java framework designed by this fellow Doug Lee, who is a professor at a small university in New York State, and he was the principal creator of Java Util Concurrent, of the stuff that you've seen in two lectures ago. And so he then went on to have a version 2 of that framework. And so one of the things that he added in was this fork join stuff. So it's in Java 7 after a long journey. And the Scala people also taking it as the basis of the actor implementation. And they're also using it for something else that we'll see today with parallel collections. And there's a pretty nice article that goes more in depth, and I show you give you the link for that. So, so in traditional applications, you had a thread per task, and so the traditional kind of application was that you had a web server, a new connection comes in, that connection runs on its own thread, but of course it doesn't really do very much. Most of the time, it'll block for something, it'll wait for I/O, it'll wait for the database, and so if a thread is not active very much, then it's okay to have lots of threads. So if the thread is only active 10% of the time, then the number of threads that you can clearly easily have is 10 times the number of processors. If the thread is only active 1% of the time, you could have 100 times the number of processors, and so on. But if you have a computationally intensive task, such as doing some computation with a large matrix or with a large array, then all of the threads are going to be busy all the time, and so then really the number of threads should be the number of processors that you have available, and then this rule doesn't hold. So the job of a fork join framework is to map lots of tasks to a few threads. And so now you can already imagine why it's going on inside the actor framework, because there you have the same situation. You have lots of actors, and then they need to be mapped to a few threads. Yeah?
How is this framework different from the executable?
You'll see in a minute what it does specially. It's made for recursive computations. So it's specifically made for something where you can break up a big problem into little. It uses. I'm sure it uses the thread pool underneath, and I would imagine it uses one of the executors. But it's more specialized. So it's built for exactly the situation that you find on this slide, where you have a problem where if the problem is small enough, you solve it directly, and otherwise you break it into subproblems, solve each of the subproblems, and you combine the results. When you have something that has this structure, then the fork join framework actively supports this. If you have something that doesn't have the structure, then you wouldn't be able to use it. So, but these are pretty common. If you think, for example, of computing the smallest value in a very large array, then you can do that a segment at a time, and then you can combine the minimum. So it's easy to parallelize. Or if you think about computing, doing some image manipulation, say some convolution of an image, you can do it in strips, and then you can combine the strips. So anytime that you have a problem that breaks up into smaller problems with this recursive algorithm, then the fork join framework will help. So it's called fork join because you fork new tasks in these recursive steps. And so this here is the fork, and then you join the results back together. So as an example here, just to see the framework in action, I extend this thing called recursive action. I have to override compute. That's just the method in the framework that that needs to be overridden. Here, say if the size is less than some threshold, this is some instance variable of my class, then I solve it sequentially. And this is also something I have to override. And otherwise, I do some kind of a split up. Here, I simply cut the problem size in half. And so here, I'm having a method that gives me a subproblem from 0 to the midpoint, and then another one from the midpoint to the total size. And I construct a new object of this max with fj class out of that. Then I call invoke all, and that takes a list of, or I think it's a bars method. It takes whatever sub problems you have, and then I combine them by getting the results. Result is an instance field that I provided. So invoke all does the heavy lifting of mapping these things to tasks and stuff. So let's look at the complete source code to see if there's anything else important in here. So here I've defined solve sequentially. And solve sequentially, of course, simply walks over the array and finds the maximum in the usual way. Of course, in Scala, I would have a method for this, but I'm just showing to you the bare bones code. To make a subproblem, I simply instantiate this thing here again, and just pass the array again. It's just a reference to the same array. I'm not copying the array. I'm just giving another reference to the same array with other index values. And over here, I say for whatever reason, I'm willing to do arrays of size up to 1,000 by hand. And here's the compute function that you just saw. So here in main, you see the mechanics of doing this. So here I'm making an array of 1,000,000 elements. Then I populate it. So here I populated with the ith element is I. So yes, I actually do know what the largest value is. It's just to see whether it recomputes the right answer. And so then I just make the entire big problem. I pass it to this fork join pool that inside itself has some kind of standard thread pool, and I call invoke, and then I get the result. So let's find out where the result was just an instance field here that gets set. Notice that each of them is a separate object that runs in its own thread, so there's no issue with two threads set this result. They live in different objects. So anytime that you have this kind of problem, you follow the same basic recipe, and you use this class, and it'll do everything for you. So that's nice. Now, in practice, what works nicely here is the following: that when you look at this particular example, I broke up an array of 1,000,000 elements, first into two arrays of 500,000, then 250,000. So it takes a while until you get down to 1,000. So you do have a fair number of tasks that are floating around. And so on my laptop, I would only have two processors. So I would have two queues that for each of the two threads that might be running in parallel. If you have four processors, you would have 4 queues, and so each of those holds tasks that get pushed on it. And so when one makes a new fork join step, then these new tasks get pushed onto this queue, and there's a particular discipline that works out nicely for load balancing. So when each thread pushes the subtasks on the head of its own It's a doubly ended queue. And that way, let's see, so the big tasks are going to be at the, okay, are they going to be at the head or at the tail? So I start pushing, so the first one here starts with 1 million, and now breaks it up into two 500,000, so they would get to the head. Then it takes it from its head and pushes then it takes this one here and breaks into 125. And so on. So you see that the one at the front gets smaller and smaller, and you see that the big tasks here migrate to the end of the queue. Now, if you have a thread that's idle, right now I already have that other thread here because I postulated that I have two. And when I have a thread that's idle, it steals a task from the end of the queue because that one is likely to be big. And so stealing is going to be fairly rare because it's going to take that second thread some amount of time to deal with this hefty task. So now if you have, like, say, 8 threads or so, you can imagine how, they all steal something pretty big, and you're pretty soon going to have a pretty balanced system. So it's a very simple strategy with almost no synchronization costs. All the tasks are isolated from each other. The only synchronization is on this deck. So one does have to lock the deck whenever one adds new tasks. But the queue that, well, actually that's not quite true. Where do we have to lock? The only way that you get something to the front of the deck is by that one thread that chops this thing into smaller ones. And the front and the back, they're isolated from each other. So you can manipulate the front of the deck if you make this as a linked list. You can manipulate the front independent of the rear. So you don't have to do any locking to manipulate the front. To manipulate the rear, yes, that does mean you have to lock, but that's pretty rare because these things are big. So there is some locking cost, but it's not very good. So you have an almost automatic load balancing with minimal synchronization. So that's a nice scheme to not have to worry about the synchronization cost, and it's quite popular. Yeah.
But why are you not dividing your tail into different tasks?
Well, the way that it always works is that when a task comes along, it grabs the front of the queue, and then it executes it. Well, what happens with those tasks? If there was one case that says if it's small, then actually do the work, and if it's large, make 2 new tasks. And so the 2 new tasks get to the front. And that's why you notice that the numbers are funny, that this 500,000 here isn't going to be dealt with for a good long time. So this 250,000 again just stays there towards the end for quite some time. So the one at the very front gets chopped into small pieces. And eventually it's going to go down to 1,000, and then they'll be dealt with, and then other fairly small things come out in the front. And all the big ones here are at the end. If I have other threads available, they're going to take one of those big ones. So it's intended that the tasks get smaller and smaller here.
So after it takes the big one, then since it's not...
Well, it'll then be in a different deck.
Oh,
Some other thread is now going to take a big one from the end. It has its own deck.
okay.
That's now going to be populated with 250,000, and then the same thing repeats. And so the rule of the game is each task will first look whether its own deck is non-empty, in which case it keeps subdividing it. And if it were to be completely idle, say because it's all done, then, so what's also somewhat likely is that that first guy is probably going to be busy all the time. But now someone here steals this one, and then the third one might steal this one, and might be finished kind of sooner, right, because it's only half the work. And at that point, then it'll steal from somewhere. I don't quite know from which other queue they steal, whether it's from the longest one.
So the dividing is going to be stop when the threshold value?
That's correct. So if we go down here to when it reaches, let's say, 1800 and make up a number, and I'll divide that quickly. Then it would divide into two 900 tasks, and it would put them both on again, and then as soon as one of them gets grabbed, then it runs into the sequential part and actually does the work. So what you're going to be seeing is some furious logarithmic making of tasks, and then one of them is actually going to occupy some amount of time to do that.
So similar thing, Intel came up with a new language called Reading Building Blocks.
I see.
It's for C++ programmers, and to make it was the exact same concept.
Okay.
Like Java speak.
Oh, the fork join frameworks have been around for a long time, and so I'm sure someone has stolen ideas from someone else. But yeah, that's normal. So ideas are meant to be stolen. Someone said, "Don't worry about someone stealing your ideas. If they're any good, you have to ram them down people's throats." That's very true. All right. So now, what's the next step that one could do to make life even easier for application programmers? So it turns out that a lot of business applications that need to work on very large data sets do surprisingly little interesting work with those data sets. Some 20 years ago, someone at IBM measured these things and said that a good fraction of what their mainframe was used for was sorting, searching, and totaling. And that was it. So they had these huge mainframes that were doing the same thing over and over again. And so can one parallelize kind of these very basic algorithms? And so Java 7 was supposed to have this. So the idea was that you should be able to do something where we'd have a parallel array of students. A parallel array is one that supports these operations. And then we'd be able to say, filter out all of the ones that fulfill some is senior method. And then we want to extract the GPA. So with mapping was what we know as map in Scala. Select GPA would be a function that extracts the GPA. Then we want to have the max of that, and that would give us the best GPA of what we know those students, whatever. And this was a great idea, except for the minor wrinkle that in Java, you don't have closures, so it was pretty painful to supply these functions. They had some syntax for it where you would have to make an anonymous object of an anonymous class, that subclass like function1 or some such thing, and everyone hated it. And there was at the time some feeling that closures were going to be coming to Java 7, but then that never materialized. And so Doug Lee said, I'm just not going to work on this part. We're just going to have to wait for some future version of Java that's going to do this. Now Java 8 is likely to have some weak form of closures, and it's the goal that they're going to be strong enough to support this kind of thing. So it's possible that we see this stuff in Java 8. But why wait? Because we can get this stuff today in Scala, and it's actually very nice, as you'll see in the lab. So here, making an array of 1,000,000 big ints. And I chose big ints because I figured the operations of them would be a little bit slow, so you'd have some would be interesting to parallel. So when I have any collection at all and use the magic dot par, then it makes a parallel wrapper over the collection that is amenable to these parallel operations. So let's look at a.par.sum. So whenever you have a collection in Scala, you know they're all very uniform and they all support sum. And to the degree that you can say hello.sum and it'll sum up the character codes in the string. So if you have an array or a list or anything, sum always works. So a.par is also a collection, and so yes, it does have a sum, but the interesting thing is it'll now automatically apply the fork join framework, the various framework that we've just seen, to cut this thing into an array of 500,000 and sum each of them until some threshold that they're determined by some heuristic. I think it depends somewhat on the number of processors. And so you, the programmer, you if you want to parallelize your sum computation, all you do is you do a dot par, and you're a genius. Right? Then it does all of the hard work automatically. Now you might say, summing is kind of pretty trivial, but it works for predicates too. Let's say I want to count all of the even ones. Then I can give a predicate. I can give an arbitrary predicate. This is just an example. And then it'll count and apply that predicate and parallelize that computation. Now that means you can do, filtering will work the same way. And that means you can do reasonably interesting computations, because you can do a lot of work, as you know, by doing mapping, filtering, and so on. So with map and filter, then of course the result is again a collection, and it is smart enough to build up the collection again in the right way. And that's actually a little bit harder than you might imagine. So let's say that I have some big collection. Now it gets broken up into pieces, and now map gets applied to give some result. And so then it'll combine the results to a big thing. If you did this poorly, this would be expensive, because then you might have to glue two arrays back into a big array, and you might have to copy elements. So what it actually does under the hood is, at this point, it knows that the result is going to be an array of 1 million elements. It pre-allocates the array, and it makes it so that these individual maps populate the subarrays, so that everything gets put in the right place. So, and we see this somewhat over here. I purposefully glossed over this part here a little quickly. Notice that over here, I have a dot par. So over here, I'm having a range, the numbers from 0 to 1 million minus 1. I parallelize that range. And so that means that this for loop here is going to be done in parallel, because when you have a for loop of the form for I goes to some collection and then some action or some body, in Scala that gets automatically translated to c.for each. So the for is just syntactic sugar for a call to for each. Now what is C? C is the parallel collection that goes from 0 to 1 million. So that parallel collection gets hit with for each. That means half of them happen in one thread, and the other half happen in the other thread. If I have 4 threads, then it gets the 4 of them happen in parallel. So what is in this case the body? The body is the action AI equals I. So that means I have this big long array, and it gets cut into some number of segments, as many as I have threads, and each of them gets populated with the right numbers in parallel. Now, if you wanted to program that yourself, like say you wanted to do that with a fork joint framework, you could, but that would be kind of a pain, right? You would have to come up with a recursive task, the subclass of recursive task, and there's a certain amount of paperwork that you have to do this. You would have to figure out, where the eyes go, and where you need to put them, and offsets, and all of that. And in Scala, 4 characters, and you're a genius. So this kind of shows the power of having a system that lets you build these very effective abstractions. So under the hood, I would not have wanted to write this stuff, because they need to keep track of how do you do the division into different pieces and all that. And they have to do it not just for an array, but for every one of the data structures that they support. Now this will work for array buffers and linked lists and maps and everything. And they've done the heavy lifting too. Some cool graduates do. So is it faster? So I wrote myself a little time utility that takes an arbitrary action, and it computes the current time. It executes the action, and it returns not the answer, but simply the difference between the end time and the start time. So when I run time on this thing where I parallelize the setting of the array, then that was done in my run in 867 milliseconds. And when I do it without the dot par, it takes 10,000. So it's not twice as fast, but it is faster. You can't quite expect these things to be twice as fast because there's a certain amount of bookkeeping. But I've kept both of my cores busy, so that was good. So the same thing with some where you can see this was actually the easiest thing to parallel. So it's possible that what you see here may well be a good part of the story of what concurrent programming is going to be looking like in the next 10 years. Because as you've seen before, where we did locks and conditions, you can do a lot of things wrong with concurrent programs, and you will painfully feel that in the next homework assignment just how many wrong things one can do. And here, you really can't do too many things wrong. I shouldn't say that. See if we have this in the lab. No. Okay, what can you do wrong? I should have put this on the slide. Yes, where can you go wrong? What's that? Yes. And so let me give you a bad way of doing something. So let's say over here I'm computing the sum in this way, right? But suppose I said so what's bad about it?
You're kind of adding to the previous sum value, so now you want to carry over the previous sum value into a previous.
So
So you can parallelize and fill in this value.
oh, it'll parallelize it, all right. It'll turn this one into 0 until a dot size dot r dot for each.
Is it that sum will be 0 or this sum will be shared between all the,
Yeah.
and so you won't get the right answer?
Yeah, I'll get an answer, but I would be very, very unlikely to get the right answer. Why?
Each will have its own sum value.
Huh?
Every time sum is modified.
So that's how computing a sum works.
So every time the sum is starting with the 0 value and then the computation.
Why? When you compute a sum, it starts with 0 and you keep adding things to it.
But the second thread, it needs to have the sum value which is the output of this previous thread's output, right? Like, and it will
Yeah.
But it is not that, it is listed 0.
Or not? How do you know it's 0?
I
So
think
zero
all
is the value of whatever it has correct time.
Yeah.
It won't be the correct time.
So you have multiple threads accessing this, mutating the same variable. That's the short answer. When you have multiple threads mutating the same variable, the results are unpredictable. And so this is what happens, right? And you don't really see the threads. They're hidden in this .par, which calls this whole machinery of the fork join framework, which cuts up your big collection into smaller pieces. And you don't really see it, but it does happen under the hood. And so yes, this is bad, bad, bad. So, yeah.
You said in the previous example, the big code, the var result equal to 0. You said each thread had its own copy of result.
Right, but that was a Java, or not a Java, but it was a class. It was a class that you started with one object, and then each object spawned two separate objects. which spawned more objects. So each of those objects had a separate accumulator. And that was fine. But over here, this code here clearly takes a global variable, and that single variable gets updated. That's what the code says, because this action here is just its code. So this is a function that we're giving to for each. That function takes a parameter I. Each time it gets called, it adds AI to that to this thing sum. How does it know what sum is? It's a closure. It has remembered what that sum thing is. So here's a problem that you have in Scala, that the compiler can't really tell you that this is bad code. And the reason is that the compiler has no sense for that the action here should have no side effects. We have a similar issue with actors, where in the act method, if you mutate some shared variable, it's also bad. And this will happen to you. At least it happened to me. Maybe you're smart, but it happened to me that when I was doing some actor solution for one of the homeworks, the numbers came out all wrong, and then I finally realized that I was being stupid, that in my act method, I mutated some global state, and I was not happy with Scala. Why couldn't it detect it? But it really can't. The Scala type system has nothing in it where you can say, this block should be non-mutating. This should be an accessor-only block. That would be a nice feature to be able to verify in the type system. But there's nothing in the Scala type system that lets you do that. So you can take these closures, you can access enclosing variables, and the type system is pretty silent about what these closures are. So that's a definite danger. And so at first, when I did this, I intuitively thought, no one is ever going to do this. And then I lectured about this to students in the Swiss summer school, and in the lab, everyone did this wrong. And it was really amazing. So everyone had the wrong intuition about how this stuff works. So it's fine to parallelize, but it's now your responsibility that all of these actions, these itty-bitty actions that you put in there, that they are read-only, that they don't mutate shared state. And so that's one reason that people say that if you have a functional language that doesn't allow any state sharing, that's a much better choice for parallel programming, because it could do these parallelizations, and then you don't have to worry about it, and you'll never fall into any of these pitfalls. So it is possible that one of the more strictly functional languages would really have an edge over what Scala can offer here. I hope so. All right. So to summarize, this is an easy thing. So this framework makes it easy to parallelize anything that naturally breaks up into subtasks. You don't have to worry about allocating threads. You don't have to worry about load balancing. It's all done for you. It's a part of Java 7, so if you have any kind of Java application where you need to do this, then all you need to do is extend this recursive action, and you're done. And the next step is to have these parallel collection classes, the classes that even do the recursive action stuff for you. And those are very nice, and they'll eventually come to Java, but right now we have them in Scala. And because in Scala we do have closures, and in Java we don't. So in the lab, it's a simple lab. All I ask you to do is, I thought I fixed this. You must set, you should do the same thing, but I want you to compute the average. And there's a bit of a challenge with the average. So if you have these numbers and you compute the average, and you have these numbers and you compute the average, and now you have to combine the results, Well, the maximum was easy to combine the results. You just took the maximum of both and that gave the maximum of everything. How do you combine the averages?
So then multiply the length and get the
Thank you. Yes, so now what you have to do is if you want to combine the two, you also need to keep track of the length, and so you have to take average times n1, average 1 times n1 plus average 2 times n2 and divide by n1 plus n2. If you knew that they had exactly the same length, then you could take the average of the averages. But if you don't know that, this one here might have, by random chance, been chopped up into one that was a little bit longer. Then you need to multiply back by the length. Alternatively, what you could do is you could not return the average, but you could return a pair consisting of the sum and the length. Or you could just return the sum and compute it. I think actually, I take that back. I made it so that you can't compute the sum. It'll overflow. So you do want to do this. All right. And in step 2, it's the same thing, just use parallel collections. Should be easy. All right. And ignore these things with the preview and release candidate. By now, 1.7 and 2.9 are on.